Hello, my name is Rebecca Muller. Today we're going to learn about a process called decomposition of partial fractions. This process is useful in areas of calculus and some other things in mathematics. Let's look at what that means now. First of all, let's consider the sums of rational expressions. We've done this previously by combining two or more rational expressions into a single rational expression. Adding these two fractions together to get a single fraction is what happens when we end up with the summation. Partial decomposition ends up reversing this process. In our example, if we add these two fractions together, we get a common denominator, change the numerators so that we have equivalent fractions, simplify in order to come up with this expression, 5x minus 7 divided by x squared minus 2x minus 3. In partial decomposition, we would begin with the fraction 5x minus 7 over the denominator x squared minus 2x minus 3 and end up with the two fractions that we had at the outset of the other problem. Now, to accomplish this, we're going to end up looking at a series of steps. We're going to give you the entire list of steps right now, but we'll also review these as we go along. Step 1. If the rational expression that we're looking at is not a proper fraction, so that we have a fraction with the numerator of lower degree than the denominator, then we need to divide f of x by g of x. In step 2, we want to factor the denominator completely. Step 3, which we'll see later, will tell us what to do if the factors are linear. Step 4 will tell us what to do if the factors are irreducible quadratics. In step 5, we'll use algebraic techniques to solve for the constants in the numerators of the decomposition. Let's begin with our first example. We want to find the partial decomposition for the following rational expression: 2x to the 5th power plus 3x to the 4th minus 3x cubed minus 2x squared plus x divided by 2x squared plus 5x plus 2. The first thing we should note is that this fraction is not a proper fraction. The numerator's degree is 5, whereas the denominator's degree is 2. In order to get this in the proper format, what we would have to do is go through a long division. I've already gone through the division process. This is a process that you should already know how to work out. And now let's see what we do once we've ended up doing the division. We can rewrite our original fraction then as x cubed minus x squared, the quotient, plus the remainder x divided by the denominator of 2x squared plus 5x plus 2. We would then work with this expression in order to continue our process. Our step 2 now, recall, tells us to factor the denominator completely into factors of the form ax plus b quantity to the nth power, or the quantity cx squared plus dx plus e to the nth power, where that quadratic would be irreducible and m and n are integers. So in essence, what we're trying to do is end up with linear factors, or if they cannot be reduced to linear factors, then at least the irreducible quadratics. Let's go back to our expression that we have in this problem. As we'd seen earlier, we've done the division and ended up at this point. We now know that we want to take the denominator, 2x squared plus 5x plus 2, and factor this completely. This is factorable into the following linear factors. We can multiply 2x times x to give us 2x squared, and if we put the factors of 2 in this order, 1 and 2, positive values, plus signs in both cases, then we end up with the factorization of that denominator. Now that we have that, we can rewrite this as x cubed minus x squared plus x divided by 2x plus 1 over times, that is, x plus 2. Let's see what step 3 tells us to do. For each distinct linear factor of the form ax plus b, the decomposition must include the term a, which is going to be some new variable, divided by that linear factor. Back to our problem, what that tells us is that in order to complete the decomposition, we're going to concentrate on this part of the fraction. We'll remember that x cubed minus x squared is part of our fraction, of our expression, that is, but actually we're going to hold off on dealing with that throughout our next few steps. We'll put it back in at the end. According to step 3 that we just read, for each of our linear factors, we want to come up with a fraction that has a numerator that is a constant with that denominator. This should look vaguely familiar to what we'd seen at the outset, where we have two fractions combined together by getting the least common denominator. Here, we're separating them back into the two fractions. Now, what we'd like to do is to take this and end up figuring out what are A and B. In order to accomplish this, our first step will be to find the least common denominator and multiply both sides of the equation by that. Notice our least common denominator will be the product of 2x plus 1 times x plus 2. Multiplying on the left gives us x. On the right-hand side, we'll have a times x plus 2 plus b times 2x plus 1. At this point, what we're going to use is the fact that the equation we had to begin with was an identity because the rule said it was. Our second equation is also an identity. But notice that in our first equation, we have some values for which the expression is undefined, namely those values which make the denominator 0. In our second expression, we're going to use those values in order to find values for x, for a and b, that is. Let's start with x equal to negative 2. If we substitute that value into the bottom equation, we'll have negative 2 equals a times 0 plus b times 2 times negative 2 is negative 4, plus 1 is negative 3. That gives us negative 2 equals negative 3b, and so 2/3 is equal to b. Let's do basically the same thing, only this time take the value of x, which makes this first denominator 0. That is negative 1/2. We're going to substitute that into the same equation that we had previously. That gives us negative 1/2 equals a times negative 1/2 plus 2 plus b times 0. Remember, that's why we chose that value, so we have a 0 here. We end up with negative 1/2 equals, and when I add 2 and negative 1/2, that gives me 3/2 times a. Multiplying both sides of the equation by 2/3 tells us that what we can end up with here is a negative 1/3 multiplying by 2/3 equals a. Now that we've gotten these solutions, what we're going to do is substitute them back into the format that we had for this partial decomposition. We had said at the outset that this fractional part of the rational expression is equal to a divided by 2x plus 1 plus b over x plus 2. We found that our a value is negative 1/3 and our b value is positive 2/3. Let's substitute those in now. We have negative 1/3 divided by 2x plus 1 plus 2/3 divided by x plus 2. In order to make this format look a little bit better, what we're going to do is multiply numerator and denominator of both of these fractions by 3. That leaves us with negative 1 over 3 times 2x plus 1 plus 2 over 3 times x plus 2. Putting this together with what we had previously, what we found out is that we have x cubed minus x squared plus the negative 1 over 3 times 2x plus 1 plus 2 over 3 times x plus 2 as our partial decomposition. Now, what we'd like to do next is look at a second example. Let's find the partial fraction decomposition of this rational expression. We have 2x divided by x plus 1 times the quantity x plus 2 squared. This appears to be the same format as what we had earlier, except as you'll notice, this factor of the denominator is actually a linear factor raised to a power. Let's see what to do in this case. What we want is for each repeated linear factor of the form ax plus b to the nth power, the decomposition must include the terms a sub 1 over ax plus b plus a sub 2 over ax plus b squared, and so on. In other words, for every power of that linear factor, we're going to have a separate fraction. Now, what that means to us in our example is that we're going to have at the outset the following setup. We will have a constant value over the first linear factor, x plus 1, plus a constant value over x plus 2 to the first power, and we'll also need a constant value over x plus 2 squared. Using the same process as we had previously, we'll multiply through by the least common denominator, which is this denominator. That gives us 2x equals a times x plus 2 squared plus b times x plus 1 times the other power of x plus 2 plus c times x plus 1. Now we need to use the same idea as we had previously. That is, let's see what happens if we take the values which make these parts of the expression equal to 0 in order to simplify. Let's let, for instance, x equal negative 2. What we end up with is negative 4 equals a times, and substituting in negative 2 gives us 0 for the first term, plus b times, substitution of negative 2 here gives us also a 0, plus c times, and when we substitute in the value of negative 2 in our last term, we end up with negative 1. Therefore, we have negative 4 equals negative c, and so c is equal to 4. We also note that if we let x equal negative 1, we can substitute into this equation and come up with negative 2 equals a times, here we're going to have negative 1 plus 2 squared, which is just 1, plus, in the second term, the negative 1 makes that factor 0, and plus, in our last term, we also have 0, so we get that a is equal to negative 2. Now, we've exhausted the possibilities where we have denominators equal to 0, but actually any value will work here. So what we're going to do is to choose an easy value to substitute in. Let's substitute in the value like 1. Actually, we can make it even easier. Well, let's make it easier. Let's plug in 0. So we're going to have 2 times 0 is 0 equals a times 0 plus 2 squared, which would be 4, plus, here we'll have b times 1 times 2, so that's going to be 2, plus, and here we end up with c times 1. Now, we have values already for a and c, and so we can substitute those in now to give us a times 4 is the same as negative 2 times 4, that's negative 8, plus, here we have b multiplied times 2, which is what we're looking for, and then plus 4. Simplifying, we can combine like terms on the right-hand side to give us negative 4 plus 2b, and then we have 4 equals 2b, and so 2 is equal to our value of b. Let's go to another screen so that we have a clean slate to start with. We have our expression, which we began with, 2x over x plus 1 times x plus 2 quantities squared, and we have the format that we knew we needed. We found out that our a value should be negative 2, b should be positive 2, and c should equal 4. Substituting in, then, we end up with negative 2 over x plus 1 plus 2 over x plus 2 plus 4 over x plus 2 quantity squared. And that's our partial decomposition. Now, we've looked at what happens when we have linear factors. But as we saw in the outset, we could also have some factors that don't end up being able to be decomposed into linear factors. That is, we can't factor them further. We end up with irreducible quadratics. Let's see what to do in that case. Step 4 reads, for each distinct quadratic factor of the form cx squared plus dx plus e, the decomposition must include the term bx plus c in the numerator over that denominator. Notice that what happens is when you have an irreducible quadratic, your numerator is linear. Also, for each repeated quadratic factor, which is an irreducible quadratic to a power, the decomposition must include each of those terms to the powers as it did with the linear version. For our example, let's find the partial decomposition for 3x minus 1 divided by x times the irreducible quadratic 2x squared plus 1 raised to the second power. Now, let's begin by setting up the correct format. What we want is for each linear factor, which we have 1, x, we're going to put a over x. For each factor of the form 2x squared, in this case 2x squared plus 1, each irreducible quadratic, we need to have a linear factor. So we have bx plus c over 2x squared plus 1. And because this is squared, we're going to have another fraction, dx plus e over 2x squared plus 1 squared. Our process, however, at this point is the same as it was previously. That is, what we want to do is multiply through by the least common denominator, which is our original denominator here. Doing so, we come up with 3x minus 1 equals a times 2x squared plus 1 squared plus the numerator of bx plus c times x times the other power of 2x squared plus 1 plus dx plus e times x. Now, what we need to do is multiply this out. We're going to look at another method at this point because of the fact that we have these irreducible quadratics involved. We're going to have 3x minus 1 equals a times 4x to the fourth plus 4x squared plus 1 plus, in our second term, we'll multiply out and end up with bx plus c. I'll multiply here first. We get 2x cubed plus x, plus we have dx squared plus ex. Continuing to solve, we'll have 3x minus 1 equals 4a x to the fourth plus 4a x squared plus a plus 2b x to the fourth plus b x squared plus 2c x cubed plus cx plus dx squared plus ex. Now at this point, what we're going to do is to equate exponents. And so in order to do that, what we need to do is look for the like terms so that we can then put those terms together. We have 3x minus 1 equals, we have a 4ax to the fourth and a 2bx to the fourth. If we combine those, we have 4a plus 2b times x to the fourth power. I'm going to go ahead and keep track of what I'm doing by scratching out the ones I've already worked with. We have a 2c x cubed. That's the only term of that type, so we can write it down in the next step. And then we've worked with it. We have a 4ax squared, a bx squared, and a dx squared. Combining those gives us 4a plus b plus d times x squared. Next, we note that we have a cx and an ex. So this is going to be plus c plus e times x. And then finally, we have a constant of a. Now, we said we were going to equate exponents, coefficients that is, and this is what I mean by that. Notice that the value of 3 is a coefficient of the x term. What that means is that the expression c plus e must equal 3. We have a constant value of -1. That value must be the same as a. For all of our other coefficients, we must end up with a value of 0 because there is no x squared or x cubed or x to the fourth term on the left-hand side of the equation. Let's write those down as a system. What we have is that 4a plus 2b had to equal 0. 2c also has to equal 0. 4a plus b plus d has to equal 0. C plus e must equal 3, and a must equal -1. In order to solve this particular system, what we're going to do is look for the easiest versions. What we note is that we already have A equal to -1. If we look at our second equation, we can note that C must equal 0. Now, C plus E has to equal 3, so 0 plus E has to equal 3, which means E must equal 3. Next, let's go to the top row where we have 4A plus 2B has to equal 0. Substituting in -1 for A gives us -4 plus 2B equals 0. 2B equals 4, and B equals 2. And finally, we had 4A plus B plus D equals 0. And if we substitute in a -1 for A, that's -4, plus a 2 for B, plus D equal to 0, we have -2 plus D equals 0, and D must equal 2. Let's take those values that we found and substitute them back into our original format. We had the original fraction in this format equal to A over x plus the linear factor over the quadratic to the first power plus the linear factor over the quadratic to the second power. These are the values for A through E that we have found. If we substitute in, we get -1 over x plus 2x plus 0 over 2x squared plus 1 plus 2x plus 3 over 2x squared plus 1 quantity squared. And this is the partial decomposition that we found. Now, partial decomposition requires a strategic way to go through things, and it's very systematic. Please take some time to learn those steps and practice some now.